Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah. Well, first of all, sorry for the jet lag. I'm kind of slow now, but I'll do my best. My name is Darío Álvarez. I'm from the University of Oviedo. This is at the north of Spain, in Europe. Oviedo is mostly known for being the hometown of Fernando Alonso, who will probably become the next Formula One world champion next Sunday in Brazil. And, well, we also have a university there. And the context of the project, I have to tell something about the beginnings. We started working on a project to build an object-oriented operating system with abstract machines in managed code. We developed our own abstract machine with a given object model, and when we were at it, we wanted to have in the system, as it would be an operating system, an access control mechanism or protection system. The idea is in operating systems, when you have to control whether a client object can call a method of a served object in object-oriented terms. For example, as it says here, a student object can call the change method of a grade object. And there are many protection mechanisms there, access control mechanisms, and we found that pure capabilities, we'll explain later if you are not accustomed to this terminology, are very good for this environment. And, well, the final statement should be for us that this kind of protection should be an integral part of the object model and not an addition after the system is built. We did a prototype implementation of our capability system into the rotor in the first RFP, and this project is kind of the next or the logical step after this. Now for some information about protection mechanisms and access control. As I said before, in operating systems, this is one of the key parts of the system, and it's to control whether a given piece of code or subject can access a resource, file, or whatever in the system. And the most widely known access control mechanism probably would be the access control list found in Unix and Windows. In an object-oriented environment, this translates into controlling if whether a client object can call a method object, as I said before. In object-oriented abstract machines, we can have the same problem, and we have to solve this also. We have different techniques. One of them is the before mentioned access control lists, and another technique is code access security as in the form of .NET. This is based on a form of stack introspection or stack walking, as it's called in the rotor code. Well, the idea is to check when you have a method call, to check all the previous stack frames to see if these precedent calls, the objects doing the calls, have the necessary rights to perform the operation. This is also found in the Java virtual machine in more or less the similar form. But there are many other access control mechanisms, and one of them is pure capabilities. And the focus of our work is to apply capabilities to object-oriented abstract machines. We did it with our own abstract machine, which is called Carballonia, And as I said before, we did implementation of this into the rotor. And a capability, in the strict sense or in the traditional sense, pure or object capability, is a very simple concept. It's just a reference to an object tied with a set of permissions on the methods of that object. And the key idea is that if you have a capability with a specific permission asserted, this is necessary and sufficient to access the method. No, you can, if you have this ticket, you can do what the ticket implies. For example, we have in Spanish a capability here which points, it's a reference that points to an object with a set of operations, and if we have the right for operation 1, 3, or whatever, with this capability you can call these operations. You couldn't call this op2 because you don't have the right asserted. So it's a very simple idea, and it has, well, quite a set of advantages and disadvantages also. So how can we apply capabilities to abstract machines? The idea, as I said before, for us is to integrate protection into the object model, not an added patch after the system is built. Or to make protection a property of the object model. We have this inheritance and so on, and we think that the last one should be protection. And it really blends with object-oriented terms rather smoothly. The idea is to integrate these permissions, this protection information, with the references in the OO systems, and the access control mechanism is integrated with the method call mechanism. As we should see here, this object wants to call the operation 1 of this object. You have to present the capability with a specific set of rights, and the method call mechanism checks if you have the asserted right for the operation call. If you have the right, then the call proceeds, and if you don't have the right, an exception is thrown. Well, you have to do a number of modifications to instructions and structures related to these references and method calls. And the good thing about this is you don't need many other instructions to do protection in the system. You just need one instruction which restricts permissions in a reference to follow the principle of least privilege. With this new instruction, you have a secure system in the sense of access control. Well, there are a number of advantages. I should pass this more, not with deeper, I mean this, well, I should skip some of this because of the time. For example, we have this conceptual simplicity, and one of the interesting points about this capability thing is that the permission checks should be, in theory, constant time. It doesn't matter you have 1 million objects or just one, because you just have to check if the permission is asserted or not, and this should be constant time. ACLs, access control list, for example, the time to check an ACL depends on the number of objects, subjects calling the resource. And this is quite an interesting thing about capabilities. Well, there's another advantage is compatibility with existing applications, as we just have one additional instruction which, if not used, the system works as before. Well, there are some drawbacks. We can skip on this and elaborate later, but there are kind of different solutions to these drawbacks. Well, here is a rationale about why capabilities for .NET, they have their own merits. And, well, we use .NET and the Rotor platform to research on protection mechanisms. Why not? Regarding the protection mechanism in .NET, the code access security, well, it's a very comprehensive and flexible system, well, but it may not fit all the possible scenarios. For example, one thing good about capabilities is that permissions are assigned on a reference-by-reference basis. It does not depend on the class of the object, on where you load the assembly, the class, and so on. You just can assign permissions on a reference-by-reference basis. That is, two objects of the same class and in the same assembly and so on can hold different permissions when calling a third object. So this is something that, well, in .NET cache should be tricky to do, and not as simple and, well, elegant, I should say. How do we implant capabilities into Rotor? Well, the initial plan was quite simple in theory, but there were some problems in the meantime. But, well, we did at least a prototype implementation, and it works quite good. We should have to add data to represent permissions in references, as this is not in Rotor. We have to modify the instructions accordingly. You have to modify the method call instruction to check references and permissions. You have to take care that when you move reference all around, the permissions are also moved with them, and so on. It's, well, this is very nasty, as you will see before next. And the easiest part was to add just another instruction to do this permission restriction in a reference. We had explored a number of alternatives to do this. I'll just comment this first one because this should be the easiest way, but unfortunately we couldn't do that. It's just to extend the structure representing the machine references. This object ref, which is defined into Rotor and should represent references all around. This is just a pointer in memory, and we thought, well, we just add this new field to this structure to store the reference, the protection information, the permissions, and everything will propagate. But unfortunately, there are many places in Rotor where pointers are used as pointers and not as object refs, so this was not possible. We explored other alternatives. I'll leave this in the slides just for information. And the final thing we did was to add this information into the objects. So we use the object structure in Rotor as the container for permissions. So when we have an object and with a number of members inside, we added another pointer to the permissions for these references. And then we have to take care of permissions for references in the activation records. We had references in local variables, in methods, are references and should have permissions. Arguments also, when you push and pop permissions, references in the evaluation stack, you also have to push and pop the associated permissions and so on. And for this we use the thread structure of Rotor as the place to put the permissions for activation records and the evaluation stack. We'll have to modify the instructions accordingly to push and pop things here and there, as well as doing what they did before. And then the easiest part, as I said before, the restrict instruction. Well, here's a little graphic about this. We have this object structure, and we have a field that points to a capabilities table with as many permissions or capabilities as members are in the object. Same for arrays. For example, we have this capabilities table for the array, with a number of references, permissions, and each references here has a set of permissions that gives the right to call one of the methods of the class of the object in the reference. We did, as said before, the same for references in execution and evaluation stacks. Here we have the thread structure with a field for capabilities in the evaluation stack, a field for capabilities in the local variables of the stack frames, and the same for arguments or method attributes. Well, this was kind of tricky because you have to have all these things synchronized, and it's very tricky to have everything right. And then we added this new instruction to restrict the permission to call a given method using a specific references, acts at the top reference in the stack, and this is just the primitive security operator in the system. And how this works in real life, as I said before, it's a very simple thing. You create an object, and when you receive the object, the reference used to create the object is with all the permission sets. You can do everything you want with this object because you are the owner. And if you can do secure computation, you will have to restrict some of these methods. So you duplicate the reference. You have another reference. You restrict the method you don't want anybody else to call. For example, the change method in a grade. And you pass this reference to the other objects. For example, to the student object. So the student now can see other things, but cannot change the grade in this object. And it's really a very simple thing. We had to change the method call to check permissions, call and callBert, and raise an exception if the permission for the method is not holding in the reference in the top of the stack. And this is the only instruction with different semantics than before. If you have the permission, there's a security exception, and if you have the permission, everything works as before. But the nasty thing is that we had to do many modifications in other places because of this synchronizing thing. When creating new objects, you have to set all the bits to 1 of the permissions. When storing things and loading things from the stack, you have to carry the associated permissions, and many other places. If you forget one of these things, everything crashes, and you have about a week watching the code and becoming mad. This is a sample code. We create a new instance. We have all the permissions, and we are the creator. And now with this same instance, we can duplicate this, but with this same instance, we restrict a given method, this message method, and then we call with this instance, with this reference, the test message, and the call would not succeed because we have restricted the test message. Well, we have this system, the performance results were encouraging, so we thought, well, we just want to know more about protection in the context of object-oriented abstract machines, performance, comparison with different methods, how they behave in real implementations and real life, and so on. So we wanted to first improve the implementation of our capabilities for Rotor, and then to develop a number of benchmarks to try to evaluate the performance of the protection mechanism in Rotor and .NET with phase 1, as I will explain in a minute, default permissions, as it comes from Microsoft, and another interesting thing with custom permissions. And this with a number of parameters, such as number of application domains, the stack depth, number of classes, instances, and so on. And to instrument real applications, to in a real application measure and know exactly how many calls are done to the security mechanisms, the time taking, and so on. And here comes the nasty thing. We did a big mistake, which was to try our system to work with all rotor elements. As I said before, we added capabilities for objects, but there are many other elements in rotor that are not exactly objects, and references are used there. For example, in struts, there are pointers to manage code and so on. And we tried to first make our implementation work with all this. And this was very, 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 very bad decision, because it was not really important for us. We just wanted to test this OO managed code. And as I said before, you have to check everything has to be synchronized, and everywhere in rotor you move a reference, you have to move the associated permissions, and there are too many places in rotor doing this. So it's very error prone, slow, it's not still complete, and there are nasty bug there we are still chasing. So we'll have to, I think, resort to the previous version and work on this. But we did develop these synthetic benchmarks, although we are behind schedule, as I said before, to exercise the machines with different domains, stack size, and so on. And the idea is just to know the time taken to check a method call with cache, in this case, in rotor and in .NET. We did a program generator with giving the value of parameters and outputting a number of benchmark programs. And the idea is to build the desired configuration, create the domains, the number of instances, build the stack, and then call a method and measure the time taken. We did this in two phases. As I said before, the default configuration with the built-in permissions in rotor and in .NET, and default policy, and so on. And for a complex configuration with custom permissions. This should be a more interesting scenario, but we don't have all the data on this yet. But we do have data on this phase one. We did about almost 2,000 runs of these benchmark programs with different configurations in rotor and in .NET, with security checking enabled and disabled, with these Fulltrust permissions, which is the default, for example, for local applications, and with specific permission sets, different number of domains, classes, methods, instances, and so on. Well, .NET is very fast. Also for this protection thing, the times were almost not measurable. With the same configuration, rotor was, let's say, 200 and .NET was less than 1. So it's very difficult to compare. And as expected, but we have to check before, the number of instances in the system is not relevant for this. The number of methods in classes and so on is also not relevant. This Fulltrust configuration is slightly quicker than with not all rights, not all permissions in the permission sets. This was also expected, but the difference is very marginal. And there's a small tendency to increase the time checking permissions with the stack size. It's really clear in rotor, but it's not that important. But we have to say that the number of domains here is not relevant with the same stack size, because the default policy assigns all the domains the same set of permissions. So this stack working thing is not as complicated as it should be with different permissions for different domains. We have some graphics here. For example, on a null method call, the code does nothing, just empty loop. Here is Rotor with Fulltrust, which is slower as expected with Rotor with the security disabled. And this is .NET with Fulltrust. As you see with the stack size with Fulltrust, this really grows a little. And this is .NET with security disabled. So the mean overhead for checking permissions is for a null method call. The call does nothing. So this should be the time taken for the code access security mechanisms to check the things is about 70% in Rotor and 200% in .NET. If the call is just about 100 times more complex than a null method call, should be 500 loop doing an arithmetic multiplication, I guess. This is the result. And as you see, there is really no difference between the checking permission things, checking the permissions, and with security off. So the cost of protection for a really simple method is near nil. In fact, it was slower checking without checking permissions. And there's some strange thing about these spikes here. We don't really understand, maybe because at given stack sizes, Rotor does something there, perhaps compress the stack or something, and this slows the thing. We don't really explain this because this should be like more like this. For example, these spikes do not appear in .NET, and here we can see a difference between checking permissions and not checking permissions. But in absolute times, it's really negligible, but it's about 40%. And for a more complex method, this is the same as for Rotor, and the behavior is just about the same for .NET, but the overhead, as the method is more complex, is just 8%. So in absolute terms, the overhead of protection is really very small. For very modest user methods, it is nil. So we ask ourselves why not protecting by default all user calls if this is free. We are still at benchmarks phase 2. It's being finished. We have a very big number of programs to run to generate this data with, as I said before, application domains with custom permissions and permission sets. We expect the behavior to be similar to this. No, in a sense, because when you have different domains with custom permissions and permission sets, each Rotor and .NET will have to do more work, intersecting things and so on. And we expect in a month or so to have these results. And I think it's more or less time to finish. So that's all. You have any questions?
Are there any questions for our speaker?
Yes, those diagrams with stack size, was that the depth of the stack in terms of the number of activation records, or was that physical size?
No, activation records.
Okay.
It's a chain of 20, 40, 60 method calls.
Because it'd be interesting to see if you actually change the size of the activation record by having a bunch of local variables where the spikes move.
Yeah, but
because it could be a page balance.
There's something there Rotor does when the stack size is a given number, but it's not present in .NET. That's it's just specific to Rotor. It's not we'll try to find out why, but it's not our main interest. We just want to measure the cost. But yeah, it's kind of strange.
In your original diagram, you had you drew it as a capability object and the object you were protecting. Did you actually try and implement it that way? Effectively have an object in the way which enforced the capability?
Here in... Here, yeah.
You mentioned the trouble of changing the references.
Yes.
Did you consider having a reference, instead of going to the object, to go to a capability object, which then references the real object?
Yeah, we have one. I don't know if is that exactly what you asked, but we had this alternative implementation was to create in a managed object an object to hold the permissions. Yes, but this had another problems because you have to modify many things also in this sense. For example, when you create an object, when you have to create the associated permissions, and when passing references in Rotor, you will have to pass the permissions object too, and the permissions object is a user object, but you are now at the level of internal Rotor. When
you have to pass two references because you reference the capability object,
yes,
and the capability object references the target object, so you still only have one reference to pass around.
Yeah, maybe. Well, we have to rethink about this, but we explore many possibilities, and we just had to select this one for a number of reasons. This was about 3 years ago. It's kind of deja vu right now. But there were reasonable things why not choosing this. It has to do, perhaps, I remember, with libraries. There are many libraries which also use references and so on, and we have to patch. I think it was because of we had to patch the libraries using these references to use this managed capabilities object, and this was very nasty thing to do also, because there were hundreds of places where these libraries use references there.
Any problems with fail calls where you actually remove the parts of this path while using the call?
Problems when removing...
When you make a tail call where you don't keep the stack frames?
No, not really. I don't think so. This was about 3 years ago, and, but no, we just the real problem was in the FJIT when using references we have to patch there to push also our thing, and in many other places. But once you have located these things for objects, because there are for structures and so on, it's very difficult. Also, you have located this, everything. Well, if you don't lose one of these, everything works. But it's kind of tricky, yes.
Okay. Thank you very much.